Now, when we are discussing this type of a problem, and we talk about the Gibbs-Helmholtz equation, all right, when we talk about the Gibbs-Helmholtz equation, we're stating that delta G is equal to delta H minus P delta S. That is the Gibbs-Helmholtz equation. So to do this specific problem using that equation, we are calculating the enthalpy. We are calculating, well, actually the change in enthalpy. We're calculating the change in entropy and the temperature, but that temperature has to be in Kelvin. So we have to convert our temperature from Celsius to Kelvin. So this is going to be somewhat of a lengthy problem because you are going to be doing 3 different things. So I guess where do we start? We just start with the enthalpy. So I know, get my equation here, that the enthalpy is delta H, and it is equal to the products minus the reactants. So as I look for nitrogen dioxide, I get the enthalpy for NO2 as a gas, 33.84 is what I'm reading. Then I look for oxygen gas. My enthalpy for oxygen gas is 0. Nitrogen monoxide is my first reactant. So I've got 90.37. And to that I add ozone, O3, which is 142.3. So this, when I add those together, are going to be 33.84 minus, I'm going to add together 90.37 plus 142.3 equals 232.67. So 33.84 minus the 232.67, and that's going to give me a negative 198.83. My label, I need to look at kilojoules per mole. Because if you remember from the video that our entropy has different labels than our enthalpy, so we're going to have to change that once we do that. So 198.83 is my delta H. Now my temperature is by far my easiest conversion because I have 25 degrees Celsius to 73.15. So that gives me 298.15 Kelvin. Nice easy conversion from Celsius to Kelvin. Now my final is going to be my entropy. So, my entropy of my first product, NO2. NO2 as a gas, and I'm looking at my third column there, 240.45. O2, my entropy of O2 is 205. My entropy of NO as a gas, 210.62. And ozone as a gas is 237.6. So I look at my numbers, just making sure that they look ballpark. They sure do. So I'm going to take 240.45, add to that 205, and I get 445.45. And I'm going to take 210.62, add to that 237.6, and I'm going to get 448.22. Now, when I subtract the second one for the first one, so I take the 445.45, and I subtract the 448.22, and I get negative 2.77 for my delta S. But that is joules per Kelvin times mole. Correct? Because that is the label that I have at the top. So that is joules, and I need that to be in what? Kilojoules. So how do I convert from joules to kilojoules? 3 places to the left. So it's going to be 0.00277. That's a negative value. Kilojoules per Kelvin times mole. So I have moved that over 3 places to the left. Now, all I need to do is plug my values into my Gibbs-Helmholtz equation. So G is equal to the enthalpy, just to keep my color codes, enthalpy was blue, negative 198.83, negative 198.83, minus, okay, my temperature, 298.15, and I'm multiplying that value. I'm multiplying that value by negative 0.00277. So when I do my math, I'm going to take 198.83 minus, put this in parentheses, 298.15 times negative 0.00277. And I come up with a value of well, let me do that again because I didn't program in a negative for that first one. I get my value for delta G to equal negative 198 .00, and that's going to be kilojoules per mole. Now, once again, I know, look, that problem took me 10 minutes to work it there. So I understand, it probably took me a little under 10. But this is a longer type of a problem, but you are going to need to be able to calculate it because certain times you'll find an easier way to calculate this because it's easier to calculate it using the second method, which is just Gibbs free energy products minus reactants, because we have a delta G column, don't we, on our data table. So it would be easier to work it using the products minus the reactants of the free energy values. However, when we take the test, you'll be specified to use the Gibbs-Helmholtz equation to calculate this. And if you do not do so, then you will miss that particular problem. All right, so you need to know how to do this both ways. Now, the second problem that I am going to work, okay, the second problem, you know what I'm going to do? Let's just do this one, okay? Let's just do this one. So I'm going to get myself a blank page here, okay? I'm going to do that problem, this very problem, using just the delta G's. So we can see how similar or dissimilar they are. So what I'm going to do is, on my problem, I'm looking at that middle column. So I am going to find, here's my equation. Delta G equals, okay, well, the standard delta G equals products minus reactants. So if I look, NO2 as a gas, what is my delta G of NO2 as a gas? 51.84. Agreed? Oxygen, delta G is also 0 for that. So that's going to be easy calculation, 51.84. Now, I subtract my reactants. NO as a gas is 86.71. And I add to that ozone, O3, 163.4. So, 86.71 plus 163.4. So I take 51.84 and I subtract from that 250.11 and I get negative 198.27 kilojoules per mole. Now, when I did it the other way, when I come back to this problem we just did, I get 198.83. So for this one, I get negative 198.27. Okay, so they were very similar. Very similar in values. But like I said, you need to know how to do both ways, because when you take the assessment over this, you'll be asked, all right, using the Gibbs Helmholtz equation or just using this equation. So know how to do it both ways. Yeah, Kane? Both. Yeah. Yeah. WebAssign will have it both ways, and I believe they specify it also. Okay, which way to work those. All right? Any questions for me?